So what we have done till now is we have registered our device driver with the kernel. We have allocated space for the device driver. We have initialized the device specific structure cdev using cdev init, and then added cdev init, the initialized structure struct cdev, to the device table. So the device table entries are now like this. Our device table looks like this. We have the device major number, we have the device minor number, we have the device driver name, and then we have pointer to the device specific structure dev, which points to struct dev, from where we access struct cdev. We have struct cdev, we initialized it, and then we added c_dev. We have made a direct access to the struct cdev. This is what we have till now. Another important thing which I explained you in device driver is number of devices. The NOD, number of devices, we have taken 1 till now. So we are registering only one device as of now in our device driver. Have a look at this. This is our device driver that we developed the other day. These are the headers. This is the declaration.h header file in which we have given the default device driver name, which is chardev 150. The major number default is 0, the minor number default is 0. The NOD, number of devices, we have taken 1. That is what we are going to work on today. And then we have declared some external global variables. This is going to be the part of our skull. The struct dev is going to be our user defined device specific structure, where all the device parameters we will keep in this structure as and when we proceed further in the device driver development. Okay, we have also used a file operation structure in which we will describe the operations that are supported by our device driver. Well, as of now, as you can see, this is empty, means till now we have not specified what operations will be performed on our device. In the initialization function, we have taken the NOD, number of devices, to be default, that is 1, only 1. Today we'll work on this. In the device driver development, the kernel provides a symbol that is exported through the kernel symbol table, and that symbol is called module param. Let's go to the appropriate header file. Inside the kernel, user src kernel version, you go to the include directory, Linux directory. Inside this path there is a file called module param. The module param defines a macro which is used to accept the module parameter. Like you have command line arguments that you take through the main function in C, int argc char star argv. Similarly, in shell scripting, you take positional parameters like $1, $2, $3, $n. Similarly, the device drivers also take runtime input parameters, and these runtime input parameters in device drivers are called module parameters, and these module parameters are accepted in your device driver at runtime. Now, what is the runtime? Ins mode. When you do ins mode, that is the moment when the device driver is inserted into the kernel and starts to run with the kernel as part of kernel. So that is the runtime when you do ins mode. So you have to supply the module parameters to the device driver during ins mode. And the module parameters are specified by a macro called module underscore param. Okay, type save helper for a module command line parameters. It takes 3 arguments: the name, the data type, and the permissions. Module underscore param. Module parameters for the device drivers are given like this. Module parameters for the device driver are given like this, using the macro called module underscore param. It takes 3 arguments. First is the variable itself. Second is the data type of variable. And third argument takes is system flags. Now, why we have these 3 arguments is what you need to understand. Var. Okay. Variable. Why do we need this variable? Because what happens, see, in C programming you have argv array. argv0 takes the path and the file name. argv1 takes the first command line arguments. argv2 takes the second command line arguments. So you have the placeholder called argv, argument vector, where the incoming parameters are stored. In shell scripting you have $1, $2, $3, $4, all positional parameters which are provided for capturing the incoming positional parameters. But in device driver development you do not have any such placeholder like argv or like positional parameters like $1, $2. You do not have anything like this in device driver development. Therefore you have to specify the variable in which the incoming positional parameters will be captured. So incoming module parameters will be stored here. Okay, then you have to specify the data type of this variable. Then you have system flags. System flags are S. We will be using S underscore I for input, read from user, group, and other. System flags which will be used to take input, enable input into the device driver, that is enable reading into the device driver. The data, incoming data, could be from the user or the group or the other applications. Okay, applications belonging to the user or belonging to the group, or applications belonging to the other. So this system flag is important for us to use. Let's straight away jump to our device driver and implement this. In the declarations, in the headers, you have to specify the header file that is required, which I showed to you just now, which is linux/module param.h. linux/module param.h is the header file, and then you have to use the macro in the initialization function to capture the incoming module parameters. So we will capture wait one second. 2, 3, 4, 5, 6 checkout for development. Okay, exit the script. Now all the programs are out for, all the files are out for editing. 1. So we have to use module param. and the headers also we have to redo it, because earlier we did not have, we had no write permissions earlier. Module param, and now in the initialization function you will use the macro module underscore param. The arguments are the placeholder number of devices whose data type is integer, and we will use the system flag s underscore input reading from user group or other. Okay, this is the flag we use. Now module param NOD value, which was being specified, which was being initialized earlier from the default value 1, it will not be initialized from the default value 1. Instead, the number of devices now will come from the script, the test script, and will be supplied at inch mode time, like this. In the test script where we are doing inch mode, in the insert driver we are doing inch mode here. So at this point here you will do NOD is equal to, how many devices do you want me to test here? Come on, somebody tell me. Say 20. We are going to enter 20 devices at a time. Okay, save the script. Now just for the purpose of testing, I will display the value of NOD here, and later on we will proceed further and do the needful. Anji, the minor number, the device's ID is minor number, and the total scope that you have for the minor number is 20 bits. So therefore the number of devices that could be given the ID is 2 to the power 20. Rest depends on system capabilities also. So we'll display the number of devices. That's all we have done, nothing much. And let's see if we are able to give the value to our NOD. Now run one for check-in, headers.h included module param.h. Then in the initialization function, capturing the module parameters using macro module underscore param, displaying NOD, that is captured using module parameters. That's it. Check out for build 2. Then number 3, build driver. Our driver is being built and the building is successful. Yes, Shrikant, tell me. What param initialization you are talking about? See this module param. We'll see. We're displaying it. See, if it takes, we'll be able to display it, isn't it? Now we have to insert our device driver into kernel. Number 4. Device driver is inserted. This is a list of our device driver inserted into the kernel already, including our driver, which is at the top. You see CDD150, our device driver is inserted into the kernel. This is DMESG. No, this is cat proc/devices, which says that device table have the entry for 238, which is our device driver. Then we check the module lists, module stack, where our device driver is right at the top of the stack. Then DMESG, we are displaying the major number and the minor number, and see this NOD20. We are able to capture the module parameter successfully, isn't it? Then after that we have to remove our device driver 5. We removed our device driver from the kernel, and the list of the module says that okay, you are able to remove the device driver from the list of device driver. Then we check cat/proc/devices. We are checking the device table now, and we see that the device table 238, the device driver is gone. Okay. And from the module list also you see the device driver is, this check is important from now onwards. Okay, now you see cleanup begin end. So cleanup function has also worked properly. Okay, now we are going to do number 6, checkout for development, and then 0 for exit the script. Well, we are able to capture the NOD numbers. So if NOD is 20, that means in the alloc CADAV region we are going to allocate 20 minor numbers and only one major number for device driver. The major number is the device driver ID, which is given by the kernel to the device driver. There is only one device driver, 238 number we are getting. Whereas the device IDs are given by the device driver to the device ID called minor number. And there are 20 devices now, so there should be 20 minor numbers. Okay. We are allocating space. We are making a device table entry for 20 devices. That means the device table that I'm talking about, in this device table you have 20 entries in total, like this. Total 20 entries, NOD number of entries, and the major number is same for all the devices. Minor number is different, 0, 1, 2, 3, 4. Why starting from 0? Because in alloc CADAV region the minor number is the first minor number. We have already specified it to be 0, taken from this macro. Next 20 numbers will be given starting from this. The next devices will be given next to NOD 20 number of consecutive numbers, starting from the first minor number. All the device driver have the same ID. Dev. We have allocated space for 20 different devs for 20 different devices. So there will be 20 different CDEVs also, 20 different devices, and 20 different initializations also has to be done for 20 different devices, and 20 different additions has to be done in the corresponding entry of the device drivers for all NOD number of devices. We have to automate it. We have done well. We have allocated space for, we have registered 20 devices, fine. And we have also allocated space for 20 devices, fine. But CDEV we did not do for 20 devices, we did it for only one device. Now we should do it initialized and add one by one for all the 20 devices. Let's do it in a loop variable. This CDEV we'll do in a loop, for loop. For I is equal to 0 to I less than NOD 20 I plus plus. You will initialize all the 20 devices. And you will add all the 20 devices one by one. So we'll initialize 20 devices. So this dev is not going to be dev. This will be dev I, dev 0, 1, 2, 3, 4 to dev 19. When you make an index into the pointer, then this arrow gets converted into dot, isn't it? So file operations also. Here we have 20 devices. So put the index here, I 0 to 19, and replace it with dot. During CDEV add also you have to do dev I, means all the 20 devices, and replace this with dot. And then second argument is the device ID, which takes major minor number. Well, wait here. What is dev ID? We got dev ID from alloc CADAV region. In this dev ID, what do you have? If you look at this dev ID, alloc CADAV region, allocate space, register your device driver with the kernel. Now this dev ID, it is a 32-bit variable, as I've already told you. It contains upper 12 bits and lower 20 bits. Major number, which is going to be 238 in our case. Minor number, which is turning out to be 0 in our case. But wait, it will go on till 19. So how can this store all the 19 variables? This dev ID that we have stored here, now it took the first value 0. It took the first value 0 from here, because this was 0. So the first minor number was 0, fine. But we have to take NOD number of minor numbers. You getting it? So therefore, this dev id, if we use it here instead of init inside the loop, second argument, it is always going to contain major number 238, minor number 0, because this is what we initialized here with major number 238, minor number coming from here 0. So this dev id cannot be used instead of add here, because it will always give minor number 0. Whereas this seed of add will be done in loop 20 times for all the 20 devices indexed by I. So this should have major number same and minor number changing every time. That we do like this. In the declaration.h, along with dev id, you declare another variable identifier with same name, same type, different name, dev number. That was dev id. Let's take dev number. Now this dev number was external, so let's declare it separately here, dev number. Now before you do cdev add and use this dev id, you have to create dev number. Okay, dev number is a variable of type dev underscore t, which will contain upper 12 bits as major number and lower 20 bits as minor number. So it will get major number from a variable called major number, which is already 238, created from here, and it will get minor number from here, I 0, 1, 2, 3, 4 to 19. These two integer variable will be merged into a 32-bit variable of type dev underscore t by a macro called mkdev. Okay. Now this mkdev works like this. mkdev, it's a macro. It takes two integers as argument, merge them, into a single variable of type dev underscore t and returns it, where this goes into upper 12 bits of this and I goes into lower 20 bits of this. Okay, so dev number value will change every time in the loop and will be used here, number. Now this particular dev id will be major number same, minor number 0, so you'll have all the different minor numbers. Okay, now the minor number which I was earlier trying to find out from here, I will not do that, comment it. And minor number which I was displaying here, I will not do that, I'll comment it. Instead, now I'll print minor number at the end of the loop like this. I will print the minor number using macro minor. We'll take it out from dev number, where I have stored the new minor number, isn't it? And now we will test our device driver and see if it works. Observe carefully this time. Okay, so save all the files and close all the files and then test your device driver, one for check-in. declarations.h. What do we declare here? Declared dev number to store device IDs of all devices, NOD number of devices, and then init.c. Initializing all NOD devices using cdev underscore init in a loop, adding all device structures using cdev add using in a loop. Updating the device ID in every iteration using macro mkdev. Okay, check out for build number 2. Number 3, build is being done and build is successful. We are writing good drivers, huh? Number 4, insert driver. Abhi pata chalega. Well, all is well till now. So we have inserted our device driver and we got cdd150 fine /cat/proc/devices displays the device table. You have 238 your device ID. cat/proc/modules displays the module stack. Your driver should be on the top of the stack. There it is. DMASG. This is the major number, and for 20 devices, these are the minor numbers for all the devices. Got that? Enter. Now we are going to remove our device driver. Number 5. We tried to remove our device driver from the kernel and from the list of device drivers. Our device driver appears to be gone. cat/proc/devices 238 gone. cat/proc/modules device driver gone. Enter. Cleanup function begin end. All is well. Enter. Check out for development. Number 6, done. Exit test script. Enter. Done. cat/proc/devices. Device driver number 238 gone. Okay. Well, this is an important step. But all is not well with the device drivers. You know what has happened is I have added 20 entries. 20 entries, all numbered from 0 to 19. In the clean.c, we have done cdev del, where I have given dev means 0th device. 0th device pointing to cdev. So I have actually removed only the 0th device, not all the devices. Isn't it? Another thing, in the initialization function, I have done file operations for 20 devices. Okay, fine, that's fine. But we have removed only one device, that is the 0th device. This is not right. Okay, because right now we are not doing any operations on the device, just like pointers. When you use pointers in your C program, if the pointer is an invalid pointer, still the program will not complain until unless you use that pointer. The moment you use that pointer, it will give you segmentation fault and your program crashes. Similarly, in this case, what has happened is you have allocated registered 20 devices and removed only the 0th device. The device number 1 to 19 is still connected inside the kernel. Later on, if by mistake any of those devices, any of those drivers or the space allocated to those drivers are used by any other kernel thread or kernel module, your kernel will crash. And you will not get any remotest idea why your kernel is crashing. Nobody will be able to troubleshoot it. So we have to remove all the 20 devices. cdev del for all the 20 devices. Here we run the for loop, which will go for NOD number of times. I is equal to 0 to I less than NOD I plus plus. You have to do cdev del for all the 20 devices. Dot. Now cdev del will happen correctly. I could have left it like this, but I don't want to crash my systems. Okay, it will crash only when you will be giving some demonstration to some other client. Okay, so it is better idea to know what needs to be done so that your kernel is stable. Fine, let's test it once more. Test script 1 for check-in. Deleting the device entry from the device table for all NOD number of devices by using cdev underscore del in loop iterating NOD number of times. Now 2 checkout for build. Done. 3 build driver. Device driver is being built and built successfully. 4 insert driver. Insert is successful. And there is your driver CDD150 right at the top of the list. cat/proc/devices shows 238 your device driver. cat/proc/modules shows you the device right at the top of the module stack, and there you have the major and the minor numbers. And now we are going to remove our device driver number 5. Device driver removed, hopefully. Yes, it's gone. cat/proc/modules displays the device table. 238 your device driver is gone. cat/proc/modules displays the module stack, and right from the top your device driver is gone. This is good. If anything goes wrong, you will not be able to remove your driver, remember. So cleanup function also not reporting any errors. Everything is fine, and we are writing good drivers. Number 6, checkout for development. Number 0, exit. Okay, coming back to our initialization function. See, what did we do? We initialized dev number with I as a minor number, and then here we are displaying minor number by fetching lower 20 bits from dev number. Obviously it will give you the 0 to 19 value, because we put 0 to 19 value one by one into dev number, lower 20 bits, then we fetch the same lower 20 bits from here and displayed it. It is just like, we storing some value in the variable and displaying from the same variable. Well, this is not a proper cross check. Okay, to do proper cross check on your devices, whether your device driver has successfully registered with the kernel, device specific structure cdev is successfully initialized and added to the device table. Okay, to do that cross check, what we do is we will display the device ID from here. Struct cdev. Inside struct cdev, we have initialized file operations. I'll show you. FOPS is equal to dev points to dev.ops. So we have initialized OPS. with our own file operations. Well, right now our file operations is empty. There is another field called device ID. We have not initialized this device ID. But if the interfaces are correct, then the kernel would have successfully and correctly initialized this device ID with the appropriate major number and appropriate minor numbers 1 to 19 for each and every devices. This time we'll try to display our minor numbers from this dev. If we get the correct minor numbers, it will be a proof of concept, and that yes, our device driver is registered and allocated and connected, and the device specific structure also connected properly, and the concept that we are learning is also correct. So let's print this time the minor numbers, not from this minor number variable, but from dev dot c underscore dev dot dev, which is this variable. Now it's a dev underscore t. It's a 32-bit variable. Upper 12 bits are major number, lower 20 bits are minor numbers. So we'll fetch the minor out of this using macro minor, like this. Now if we get the correct minor numbers, that will be the proof of concept. Okay, let's see. Test 1 second as proof of concept and test for all registration, allocation and interfaces. We check or display the minor numbers of the devices using struct cdev के अंदर there is a variable called dev. Okay, 2 checkout for build, 3 build device driver. The device driver building is successful. 4 insert driver done. There is your device driver CDD150 right at the top of the list. cat/proc/devices shows you the device table 238 char dev 150. Here it is. cat/proc/modules. Here it is. Device driver inserted. 0 means not being used by anyone as of now. So, oh, we have the minor numbers all displayed correctly. Did you see that? We did not initialize this dev field because our cdevs got connected at the right entries for entry number 0 to every 19. All the cdevs got correctly listed, initialized, connected to the appropriate minor number 0 to 19. Therefore, the dev field took the values from corresponding minor numbers and got initialized internally, and that is why we are getting correct minor numbers now. Got that? Remove driver number 5. Checks becomes important. Don't skip it, okay? 238 gone. 238 gone. CDD150 gone. Cleanup okay. Checkout for development, not now. Over and out. This is what we do in insert module. Okay. Any questions you have, you can ask me now before I end the session for today.